So another way that we can analyze the motion of a pendulum or a mass on a spring is to consider the energy that occurs, those energy transfers that are happening as it goes through that repetitive motion. And they're actually pretty similar. In both cases, you have potential energy being converted to kinetic and back. The only difference is the type of potential energy that we have. But they both just represent this oscillation between potential energy and kinetic energy as the object goes through its motion, both in the case of the spring and in the case of the pendulum. So if we look at the pendulum here, obviously it swings up to some height, so it's going to have gravitational potential energy at its amplitude, at its maximum displacement, which gets converted to kinetic when it reaches this equilibrium, and then back to gravitational potential when it goes up on the other side, back to kinetic when it goes back through equilibrium, and then finally completing that oscillation going back to gravitational potential. With the mass on a spring, we're starting with spring potential, obviously, instead of gravitational potential. That's becoming kinetic, going back to spring potential when it's at its maximum compression on the other side, back to kinetic as it swings back through its equilibrium position, and then ending where it started with spring potential energy at its maximum stretching position. So we're going to take a look at the pendulum in positions A, B, and C that we saw on the previous page, and we're going to go ahead and complete the energy bar chart for the pendulum in those positions. So as we said, it starts with all gravitational potential energy. Okay, that gravitational potential energy then is converted into kinetic at point B, so we'll put our bar there for point B as all kinetic energy. And then when it swings back to that maximum displacement on the other side, we are back to all gravitational potential energy once again. And so that's what our energy bar chart would look like, just going from gravitational potential to kinetic back to gravitational potential energy. All right, so let's work through a practice problem here, continuing to use what we know about simple harmonic motion, specifically a mass on a spring here, and then also kind of incorporating some of the things that we just learned about energy stuff. All right, so let's start. We have this inertial scale, which we actually have talked about in the past. And basically, it's a mass on a spring. In this case, it's an astronaut oscillating back and forth on a spring used to determine their mass or weight while they're in space. And so we know the mass of the astronaut here. We know they're oscillating at a frequency of 0.5 hertz, and they're pulled back a distance of 0.4 meters, which is going to be our amplitude. So the first question is we want to know what the spring constant is. So what I'm going to start with is I know that frequency is just 1 over the period. So I can say that 0.5 is 1 over t, which means my period here must be 2 seconds. So using that period, I can then determine the spring constant using the equation we have that relates the period for a mass on a spring to the mass and the spring constant. So we can say 2 equals 2 pi times the square root of 150 over k. I'm going to divide by 2 pi. Just be careful you put that in parentheses when you do it in the calculator. And I end up getting here 0.318 equals the square root of 150 over k. Squaring both sides, multiplying by k, I end up getting 0.101 k equals 150. And so I find that my spring constant here is going to be 1,480 newtons per meter. So that answers part 1 of my question here. So that all is old stuff that we could have done before. Moving on to the next part, I'm going to start thinking about what we just introduced, the idea of energy. So I'm going to start with E initial plus work equals E final, and I'm going to use that to figure out the maximum speed of the astronaut. So I know that when they start, they have all spring potential energy when they're at their maximum displacement. There's no work being done here by any non-conservative forces, and when they get to their equilibrium position, which is where they're traveling the fastest, all of their energy has become kinetic. So I can say 1/2 kx squared equals 1/2 mv squared. I know my K is the 1480 I just found. X, when all of our energy is spring potential, that's the amplitude, is going to be 0.4. I know my mass is given as 150, and I can use that to find the velocity. So this left side of the equation ends up becoming 118.4, which is equal to 75 v squared. And I find that v then, solving for that, divided by 75 and taking the square root, is 1.26 meters per second. So there is my velocity of the astronaut at that equilibrium position when they have their maximum speed. Lastly, I want to know what is the maximum acceleration experienced by the astronaut. And so what I would think about to start here is what is the force that is causing the astronaut to accelerate. And in this case, it's the spring force. All right, so I'm going to set up my F equals ma, knowing that the spring force is the thing ultimately bringing the astronaut back to equilibrium. So that spring force is going to be equal to the mass of the astronaut times the astronaut's acceleration. I'm going to use the spring force at that point when I have the maximum force in order to get the maximum acceleration, and that occurs at the amplitude. So when I go ahead and plug in x for this situation, I'm going to use my displacement when they're at the amplitude, the maximum displacement, to result in the maximum spring force and therefore the maximum acceleration. So I end up finding that 592 is the maximum force. And when I solve for acceleration, I get that my acceleration from that force would be 3.95 meters per second squared. All right, moving on to the next and final piece of simple harmonic motion. We're going to talk some about graphing with simple harmonic motion. And so what we end up having with that is, if we look here, we have the position, velocity, and acceleration versus time graphs for simple harmonic motion. And what we see is they're all sinusoidal. This is something that you've talked about in math class, what it means for a graph to be sinusoidal. Obviously, it's either a sine or a cosine function, and it's just going to repeat itself. Okay, so we see, and that makes sense given the motion we're talking about. Simple harmonic motion is, by definition, a repetitive motion, so it makes sense that the graph would also be repetitive. So we see here for the displacement, it starts repeating itself at that period, which is t there. And same thing for velocity and acceleration. Right? We're going to dive a little bit deeper into these and talk about a few important pieces you should notice, but for now we just need to know that they are sinusoidal. All right, so let's dive a little bit deeper into these graphs. We first want to ask ourselves at what position is the object when velocity is at a maximum. We can answer this a few ways. The first is we know that velocity is at a maximum when we're at the equilibrium position, so that would be this point here or this point here. And we see that corresponds with velocities that are either at the maximum positive or maximum negative value. Okay, so that's one way we can answer that question. We know just in general that we're going to have a maximum velocity when we are at equilibrium. The other thing we can think about is we know that velocity on a position versus time graph is just the slope. So we can ask ourselves, when is the slope the greatest? And that's going to be right in this region. That's the greatest negative slope we have. And right in this region here is going to be the greatest positive slope we have. So when our graph is the slopiest, that means we have the biggest possible velocity. And that happens at these equilibrium points when the displacement is 0. Okay. We also want to think about when our acceleration is at a maximum. All right. And so again, just like we did before, we can think about either just what we know about simple harmonic motion, and that is that the maximum force occurs when we are at our amplitude at the maximum displacement, because again, that force is directly proportional to the displacement. So the more displacement we have, the more force we have, and therefore the more acceleration. And we see that when we are at these maxes or mins, the greatest positive or greatest negative displacement, that matches up with our maximum values for our acceleration. All right. The other thing we can see, and this one's a little bit more of a stretch, but knowing that acceleration represents the curvature of our graph, all right, we actually do see that our graph has the most curvature at these maximum points, right? It's pretty straight in here. It's pretty flat, no curvature at all. We have the most curvature at these maximum displacement points, and therefore that ends up being the maximum acceleration. All right, our final question here, we want to know what is the acceleration when it's at its equilibrium position. So we can either match up the displacement when we have zero displacement to those points on our acceleration graph and see that our acceleration is zero at those points. But we also can think about this in a few other ways. Number one, we know that the restoring force for simple harmonic motion is proportional to the displacement. So if we have zero displacement, that means we have zero restoring force, and that would match up with zero acceleration. We can also look at this from a graphical standpoint, okay? When you have your velocity versus time graph, which is this graph here, all right, we know that the acceleration is just the slope of that velocity graph. So let's think about our velocity points at equilibrium. That would be the maximum positive and maximum negative velocities that we've circled here. At those points, that maximum negative or maximum positive velocity, the slope is zero at that point. It's where it's changing from having a positive acceleration to a negative acceleration. And so at that point, we have zero acceleration. All right, let's work through this practice problem here. So we have a graph shown, and we have a number of questions, and we're going to be interpreting the graph and using that to answer some of these questions. So the first is, what is the amplitude of this oscillation of this 1 kilogram object oscillating on a spring? And so we see up here, the amplitude is the maximum displacement, which we can see from the graph is just 4 meters. For the second question, we're asked about the spring constant, and so what I'm going to do is two things. I'm going to interpret the graph, and so I'm going to find that the period, this point here where it begins to repeat itself, is 0.5 seconds, and I can use that period in my equation 2 pi times the square root of m over k to solve for the spring constant. So I can say 0.5 equals 2 pi times the square root of 1 over k. So coming up here, I can say 0.796 equals the square root of 1 over k. I'm going to square that and then cross multiply, and I find that k in this case is 157.9 newtons per meter. Moving on to the last question, was the maximum speed? And for that, I'm going to be thinking about energy, similar to what I did in the last problem. So I'm going to be thinking about E initial plus work equals E final. We're starting with spring potential energy and transferring all that to kinetic. So 1/2 kx squared equals 1/2 mv squared. So we can say 1/2 times 157.9. And then my displacement is going to be 4, because that's when we have our maximum spring potential energy at the amplitude. We know all of our energy is spring potential there. And so that's going to be equal to 1/2 times 1 times v squared. This left side ends up becoming 1263, and that's equal to 0.5 v squared. So I solve for v, and I get 50.3 meters per second. All right, so now we want to draw the matching position versus time and velocity versus time graphs for this motion. So I'm going to start by just remembering what I just found in the previous problem, which was that the maximum velocity was 50.3, which I'm just going to call 50 for the purposes of this graph, meters per second. So that means the maximum negative value I'm going to have here is negative 50, and the maximum positive is positive 50, and that's going to kind of help to frame my graph here. Now I want to think about where I'm starting. So when I look back to my position graph, I start at equilibrium, which we know will either be a maximum positive or maximum negative velocity. But since the slope is initially positive, that tells me that for that first part, going up to the peak here. We're going to start at a maximum positive velocity. By the time I get to this point here, that is a maximum displacement, which would be 0 velocity. So I'm going to have a 0 velocity point down here. Then we reach this point here, which would represent maximum negative velocity. So I'm going to be all the way down here with my maximum negative velocity. Then when I get to that maximum negative displacement, I'm back to 0 velocity, so that's this point right about here. And then finally, when I reach one full period at 0.5 seconds, we are back to equilibrium and maximum positive velocity. And I'm not going to do that for every single point, but that's just going to help me frame my sketch, because it's just going to repeat itself from there, something like that. We see it's repeating every 0.5 seconds. And so that would be our sketch of the velocity versus time. Now, the acceleration versus time, I don't have, as of now, the maximum acceleration. However, I can pretty quickly find that doing my F equals ma. All right, and I knew that my k value to find my spring force was that 157. I already found that, and so I can just take that 157, which is my k, times my maximum displacement, and use that to solve for my acceleration. And so I'm going to find that my maximum acceleration, which again is just going to be used to frame this, is 628 meters per second squared. Now it did technically say just sketch the graph, so not labeling them is not the end of the world, but it's relatively easy to find here. So I'm just going to add in that maximum positive and maximum negative acceleration and go from there. Going back to my position graph, I'm starting here at an equilibrium position. All right, that's my initial point, which means that my acceleration will also be 0 because there's no displacement, there's no force, no acceleration. I then am going to think about what ends up happening. And what I see here is this next portion, we are concave down the whole time, which is indicative of a negative acceleration. So that means I'm actually moving to this point here, which is my maximum negative acceleration. Then I'm back to equilibrium in the middle, so back to 0 acceleration. Then I move into this portion where it's concave up, which indicates a positive acceleration. So I'm going to hit my maximum positive acceleration right about there, and then back to 0. And what actually ends up happening with the acceleration graph is it is the complete flip of the position graph, because whenever you have a positive displacement, your acceleration is negative back towards equilibrium and vice versa. So once again, once you kind of sketch out that basic frame, you can then just fill in the charts, and I'm not going to sit here grading exactly how sinusoidal your graph is, but you should see it repeating at those even intervals, and it should look curvy, not like a zigzag line. So that's what the sketch would look like. Again, you don't necessarily have to label those, but it's nice to show how you could take it one step further here. All right, so for our final problem here in the simple harmonic motion unit, we have an old AP problem from, I think it was 2 years ago, maybe 3. And what we're trying to do here is we're looking at a situation where we initially have a block here, block P, that's oscillating back and forth on a spring, and we're going to drop a second block Q on top of it, so that then we ultimately will have a single block with a mass of 3m on top of this. And that's going to be oscillating back and forth. And so what we want to do is first determine the ratio of TP when it's just block P to TPQ. So what I'm going to do here is I'm going to set up an expression for each of those periods. So TP is going to be 2 pi times the square root of m over k. I don't know m or k, but that'll be enough to ultimately get this ratio. And then the new one, TPQ, is going to be 2 pi times the square root of 3m over k. Our spring constant hasn't actually changed. All this changed is our mass. So when I go and do that ratio, which is really just a matter of dividing those two equations, I end up getting 2 pi times the square root of 3m over k divided by 2 pi times the square root of m over k. And so we can go ahead and a lot of things divide out here. The 2 pi divides out, the k's divide out, the m's divide out, and what we ultimately end up getting here is this ratio of TPQ to TP is just equal to the square root of 3. Okay, you don't necessarily have to get a decimal form of that, saying the square root of 3 is enough to call it a numerical answer for that ratio. All right, for the second part of this, this is one of our clear, coherent paragraph length response ones. We want to know what happens to the amplitude of oscillation in this new system, and I think we probably can surmise that it's going to be less. The trick here is going to be explaining why it is less. So I'm going to do a little bit of math. You do notice that we can use diagrams and or equations in our clear, coherent paragraph length response. So I'm going to do a little bit of math and think about a few things here and then type up an explanation. So the first thing I'm going to think about here is conservation of momentum. And the reason I'm thinking about that is because we have basically a collision between these two blocks. All right, so we initially have a mass or block M moving at some speed. We'll call it V. And then afterwards, the two blocks stick together, so we really have M plus 2M moving at some new speed, VF. And so we end up with MV equals 3MVF. The M's are going to divide out here, okay? And so we can say V over 3 equals our final velocity. All right, so we have 1/3 as much velocity. In terms of amplitude, amplitude really kind of relies on an energy thing. All right, so if we think about the energy that we have, initially when it was just P, our energy was 1/2 mv squared. Now that it's kpq, it's going to be 1/2 3m, because it's 3 times as much mass, times v over 3, that quantity squared, which ends up being 1/2 times 3m times v squared over 9, which that 3 divides out one of those 3's. And what we ultimately end up getting is that our new energy is going to be 1/3, just pulling this number out here, times our original energy. And so we can say that the energy is 1/3 as much, and that ultimately means if the kinetic energy at equilibrium is 1/3 as much, that kinetic energy becomes spring potential energy. So if we have less kinetic energy, all right, our K hasn't changed, the end result will be our maximum displacement will decrease. You probably didn't need to do all the mathematical pieces of that, but definitely in terms of the concepts, I think all of those are needed in the explanation. So if we want to do just purely a conceptual explanation, what I would start by saying is when the block Q is dropped on top, we have an inelastic collision, which means that the momentum of the system is conserved, and so the velocity is 1/3 of the original since the mass is 3 times as much. I think that's a fair statement to say if you don't necessarily have the mass to back it up. And then we can say, and this is really the important piece, because it's an inelastic collision, we know that energy must have been lost in that collision. And therefore, the kinetic energy of the two-block system is less than the original kinetic energy of the single block. That kinetic energy ultimately becomes our spring potential energy, and since it has decreased, it means that the spring cannot stretch as far at its maximum displacement when all of its energy is spring potential, and therefore that means that the amplitude of our two-block system must be less than the original. All right, and that last sentence is really important because that's that thing that kind of ties everything back together. So you really want to make sure to get that final point, and that is one of the points for this problem. You have that final bit tying it all back together. In case you're curious, here's the official AP scoring guide. Probably not a bad idea to take a quick look at this, just so you get used to what these look like, and think about what they're actually looking for in terms of specific points, especially in something like the paragraph length response. So I'll just put that up there. You can take a look at it as much or as little as you want, but I do think it's a good idea to at least give it a quick read over.